Hello everyone! The intention of this video is to get you ready for your mid-chapter 8 test coming up at the end of this week. So what you'll notice that I have here first, and what I want you to have in front of you as well, is your 8.1 homework, which the sub should have handed back out to you, assuming you turned it in last class. If you didn't turn it in last class, then you probably still have this somewhere in your possession. You can take it out and kind of follow along. Just so that you're not super lost. I'm not going to dwell on this homework assignment because I've already posted the answer key to Google Classroom for you to look at in detail, but I do at least just want to talk about a few brief points of the particular questions that I graded for, I spot checked for correctness, and some other main features of just mistakes that I saw when I graded these papers. So you'll notice number 3 and number 5 are the first couple that I graded on the front side. And for the most part, all these were fine on most of your papers. One of the biggest points that I wanted to talk about was making sure that you graph the asymptote for your exponential functions. And then particularly for 3 and 5, some of you were not very careful with plugging in some numbers. Well, I'll get to domain and range in just a second. Let's talk about plugging in numbers, because I know that's kind of where some of us get stuck. You can plug in some numbers, and then at other times you're like, wait, my numbers are way too big. I don't even know where they go. The idea when you're trying to figure out how to graph an exponential is you essentially need to ask yourself what makes the exponent equal to 0. And then start there, right? Because we know that anything to the 0 power is just 1. So for instance, if you look here, like in number 3, x to the 0 power would end up with a y value of 3. So that one's good to pick. Number 5 is a little bit different, and I saw some of you struggled on number 5 because it had so much extra stuff. But essentially the question you want to ask yourself for number 5 is this: what value of x would make this exponent equal to 0? And that would be 3. So some of you started way too small. You started at like 0, and then you had really difficult numbers that were not easy to graph. But if you start with 3, then you end up with 1/4 to the 0 power, which is 1, and then you end up with -2. And then from there, go a little bit to the right, maybe 1 to the left. So essentially, when you're graphing these exponential functions, you need to ask yourself what makes the exponent equal to 0. The other thing is for those asymptotes, remember, if the equation of your exponential is y is equal to a times b to the x minus h power plus k, your asymptote is directly related to this k value. So that's why, like numbers 1, 2, and 3, the asymptote was the x-axis, and even number 5. But like for number 4, you couldn't see the asymptote because it was way down at -8. But then number 6, the asymptote was down at -5. So general observations for these types of questions is be mindful of the asymptote. And then in terms of what numbers to plug into your table, ask yourself what makes your exponent 0, and then start there. Next section, I know these were a lot tougher going backwards, and some of you skipped them altogether, which shame on you. You shouldn't skip anything, because again, the least you could have done was recognize where the asymptotes are. For number 8, the asymptote here is up here at 5, which means we know that the k value is going to be +5. Number 9, asymptote is at 0. 10, asymptote is at 3. So you could have gone there. The main thing that you need to do for these is recognize the dilations. And for those dilations, you essentially want to pay attention to, you want to pick 2 points, and you want to pay attention to the change in the y values. So for instance, if you look at, so I've got these 2 points here. This is the transformed function. I have 1, 1, and I have 3, 4. So what you want to do is you want to, first of all, we already noted that there's no asymptote shift, so that's good. And it also doesn't, it looks like it could have been shifted to the left or to the right, which is where my other possible function is coming from. But the other idea is to look for a dilation. So if you actually look at the table, then you're going to compare the same two x values from the function. So we said x was 1 and 3. You want to compare that to the parent function, 1 and 3. And so the corresponding y values are usually 1 and 4. Well, 1 and 4 are 3 apart. And notice in the transform function, they're 6 apart, which means there could have been a dilation from the parent function to this transform function of being divided by 1/2, which is why one of the answers is 1/2 times 2 to the x power. The other answer is 2 to the x minus 1 power. In short, these two equations are actually the same thing, even though there's a dilation in this one and there's a horizontal translation in this one. If you look at, all right, I'm going to take this one and bring it down here. If you look at 1/2, and I rewrite 1/2 as 2 to the negative first power times 2 to the x power, and then the rule for exponents is that you add them, right? So then this would be 2 to the negative 1 plus x power. Well, if you just change this to negative 1 plus x as an x minus 1, then you end up with this function. So in certain cases, there are actually a couple of different answers depending on just these exponent rules, so to speak, and how they can work, but neither one is more correct than the other. I know these are a little bit challenging. Know that they are not heavily going to be focused on this test. So if these gave you trouble, fear not. The ones that I care about the most from this homework are going to be 1 through 6. If you can do those, then you're on track. The backside of this was a Mod Podge of backside's over here. A Mod Podge of review questions, a few of them from SAT, ACT, and then the bottom few from Chapter 7. First of all, shame on you if you left multiple choice questions blank. Even, on the ACT, SAT, your goal is to just give your absolute best educated guess. In short, again, you can look at this answer key in detail later, but in short, for number 11, you had similar triangles. You needed to use proportion rules there to figure out what PO should be. Number 13 was a little bit of algebra, setting up equations to solve for the amount. Number 12, we did these exact types of questions a few chapters ago where you talk about one binomial representing your number of students, and then based on the money dropping, you would have your second binomial represent the cost. When it talks about the maximum dollar sales, I actually plugged this in my graphing calculator. Your maximum is going to be your vertex point, which your vertex point is found by doing negative b over 2a. And then that would let you solve for x, which you then plug back in to figure out the cost. Number 14, we're really going to get to these types of questions in a couple of chapters when we talk about rational functions, but you may have seen them before about one person working a certain amount of hours, the other one its own amount, and then how long would it take for them to work together. So I was hoping you at least might be able to ballpark reasoning an educated guess for this one, if not being able to do the actual algebra to get there. The last few at least should have been more familiar to you because it comes straight from last chapter. 15 for the most part was fine on yours. I did grade 16. I didn't highlight, but I did grade number 16 as a part of this one. The correct answer should have been x is greater than or equal to 21. And essentially what many of you did was, I didn't even have it written originally, but many of you also added this element here, which is that you put that what's inside the radical must be greater than or equal to 0, which you're totally right because we don't want any imaginary numbers. So whatever's inside the radical must be positive. But when you end up with that answer as being x is greater than or equal to negative 7/2, this just ensures that you're not going to get any imaginary numbers. This, though, when you actually solve the inequality, is your answer. Your answer is definitely greater than or equal to negative 7/2. So there's no need for this inequality anymore because your actual answer satisfies that you won't get any imaginary numbers. So that's why for many of you that wrote both of these, I took off a couple points because you only need this inequality. For number 17, I did a check. I kind of got ahead of myself. Don't pay any attention to this. You should have just gotten down to the inequality y is less than negative 4/3. And then number 18 was kind of a challenging question, but hopefully you at least were able to do a couple of steps on that and end up with this final answer down here. 3x times the cube root of x squared plus 4x squared times the cube root of x squared. Even though these are like terms, your radicals match. You can't really add your terms out front because those don't match. One is an x, the other is an x squared. Okay, moving on to our next homework assignment. This is 8.2. I would like for you, you're going to turn this in on test day, but I would like for you to grade this as we normally do. You're going to put two numbers up on top. There are, I believe, 20 questions on this homework assignment. So the first grade that I want you to put is just out of 20. How many did you complete? Hopefully you completed everything, but how many did you complete out of 20? And then the next grade is going to be correctness, and we're going to spot check 4 of them. So at the end, you'll come back and you'll put that numerator. How many did you get correct out of the 4 specific ones that we spot checked? Okay. Hopefully these should have been a little bit easier. You're going to notice my original answer key just had the pin marks, and then third period yesterday that asked specific questions, I went through and did this other stuff in blue. So for some of these that aren't worked out completely, you may need to just relook at your work / ask a friend where these answers came from if you still cannot figure them out. The first one I want you to grade for correctness in this first chunk is number 5. You should have gotten x is equal to -1/13. So remember, the bottom line in all of this, guys, was that you needed to rewrite your bases to match. If you end up getting matching bases, then we know that the exponents are also equal to one another. So that was this idea here. Again, you have this answer key on Google Classroom, so if you need to spend more time with it, checking answers and just figuring things out, you can look there as well. But for the sake of getting to today's lesson, I'm going to scroll pretty quickly. The next one I want you to check is number 9. Except I'm going to go back here for number 7 and talk about something that I wrote. I think a few of you were asking yesterday in class, or a couple days ago in class, if A and B are both 5, can you multiply 5 times 5 and get 25 to the x power? Well, absolutely not, and I've already have it crossed off here because of PEMDAS, right? Your exponent will be operated first before you would multiply by this 5, okay? So PEMDAS says that A and B cannot be multiplied. You would just leave them as is, raised to the x power. So again, you're grading number 9, 3/4 times 7 to the x power. The next 3 are essentially like the first 6. The only difference is that these are inequalities instead of equations. So just be mindful of the inequality symbols throughout those. The next one that you are grading, lost the second page. Here it is. The next one that you're going to grade is number 15, which should be x is less than -7/9. And then number 16 is worked out here for you. T is equal to 38. Talking about number 17, I originally made a mistake because I did not read, which is what you guys tend to do sometimes. Number 17, it says interest is compounded weekly. There are 52 weeks in a year. Originally, I put 12. I did monthly, so I scratched that out. The correct answer should be $16,755.63. Of course, there's debate in terms of how to round. I'm okay with you just following regular rounding rules for that. I do want you to grade number 18 for correctness. All right or all wrong with a little leeway in that decimal. And then 19 and 20, the questions about hot chocolate and the ideal temperatures. Essentially, those were just plug and chug. You had to plug in particular values for T, and that was all calculator work. So that shouldn't have been any issue there as long as we can make use of the little caret symbol to raise something to powers that are other than 2 or your typical powers. All right, so that's a recap of 8.1, 8.2. The last section that we're going to cover before your mid-chapter 8 test is 8.3, which is over logarithms, which you probably have heard before because they go hand in hand with exponents, but you probably have not worked with them as much as, definitely haven't worked with them as much as exponents. So you can just go ahead and title this section in your notes, Logarithmic Functions. And the thing that I need you to remember about logs, or learn about logs, I say remember as if you've heard it before, but you might not have, is essentially logarithms are just different representations for exponents. Different representations for exponents. Okay. Another very important factor we're going to talk about in detail in a moment is that logarithms are inverse to exponential functions. So not only are they just a different way to write exponents, they're actually the inverse to exponential functions. So by definition, this is one of the biggest things that we're going to talk about today. By definition, if I define an exponential equation, b to the x power is equal to y. Earlier last week, we talked about b being the base, your big base number of the exponent, x superscript in the exponent equals just some number y. If I claim, so we would say that this is in an exponential form, because it has an exponent. But I'm going to go ahead and say that this is synonymous or interchangeable with the following logarithm. Log base b of y is equal to x. And I highly recommend you going ahead and writing what the heck I just said, because you need to be familiar with saying those things as you read logs as well. You say this, log, literally say the word base b of y equals x. Log base b of y equals x. In the same way that x is a superscript in the exponential, b, little b, is like a subscript. And notice it's the same base. That's why it's important for you to understand in the exponential, b is a base, because in the log, it acts as the base as well. This is called logarithmic form. Logarithmic form. Okay, so this is just definition. This is the biggest takeaway from today. If you don't know this, then none of the rest of this lesson will make any sense whatsoever. So let's do a few examples. The first thing I'm going to ask you is to write the following in logarithmic form. Write the following in logarithmic form. Shorthand these directions if you wish. Write the following in logarithmic form. For example, number 1. 5 squared is equal to 25. So this is just an exponential statement. You know it is true. If I ask you to write this in logarithmic form, the main number I'm concerned about is the base, right? So the base here is 5, so then I know that my logarithm is going to be log base 5 of, again, I'm just using this puzzle here, the y is synonymous to what it's equal to. So log base 5 of 25 is equal to x, which is the exponent, 2. And that it would be the logarithmic form for that statement. Number 2, same directions. 2 to the negative third power is equal to 1/8. In logarithmic form, this would be log base 2 of 1/8 is equal to negative 3. Okay, for the next group, we're going to go backwards. I want you to write the following in exponential form. Write the following in exponential form. Number 3, log base 4 of 2 is equal to 1/2. Now, I will say in experience, people's wrong tendency is to just raise like 4 to the second power is equal to 1/2 because it looks like 4 is being raised to the second power. But obviously that's not true, right? 4 squared is 16. So the base is the same. If this is base 4, then the base of our big exponent is going to be 4 to the 1/2 power is equal to 2. And the other thing is, guys, it should make a true statement. If you put the numbers in an order that you don't end up with a true statement, then clearly you messed up the order. Last one like this, number 4. Log base 3 of 729 is equal to 6. If I ask you to write this in exponential form, that would be 3 to the 6th power equals 729. Okay, so that's just changing forms back and forth between logarithmic and exponential. If we take this a step further, I can ask you to do things like evaluate each logarithmic expression. Evaluate each logarithmic expression. So number 5, I can ask you to evaluate log base 2 of 8. Now, what I'm going to recommend that you do, at least until you get the hang of it, is literally to add in your own equal sign to this. So log base 2 of 8, if I wanted you to figure out what this expression equals, then I could literally say, okay, well, this equals some value x. And then if you then take our rules that we just talked about up top, if I rewrite this as an exponential, then that's the same thing as me saying then 2 to some power x is equal to 8. And then hopefully from there you would say, oh, well, x is just equal to 3. Let's do another, number 6. Log base 12 of 1/12. If I want you to simplify this expression, you would say, okay, this expression is just equal to some number x. Again, if you follow the exponential to logarithmic and vice versa rule, then you would say, okay, the base is 12, so then 12 to some power x is equal to 1/12. Therefore, x would equal -1. Number 7, log base 9 of 1. So this question is essentially, again, you'd probably get pretty good with not having to write equals x every single time. The question would then just kind of turn into something like 9 to what power gives you 1? And of course, anything to the 0 power would give you 1. Okay, a few more like this. Number 8. Log base 2 of 1/32. So this question would then become 2 to what power gives you 1/32. Therefore, x would equal -5. Number 9, log base 2/3 of 4/9. This question becomes base of 2/3 to what power would give you 4/9. Well, don't get freaked out with the fractions. 2/3 to some power is equal to 4/9. Notice these are both squares of 2 and 3. Therefore, x just equals 2. 2/3 times 2/3 gets us 4/9. And then number 10, log base 2/3 of 9/4. So this is a little bit different. Same idea. You can rewrite it and ask yourself, okay, 2/3 to what power gives me 9/4 now? Well, if you kind of take what we learned from number 9, this is just the reciprocal of 4/9. Therefore, we know that x must be the negative version, aka -2 of that. This is a good point of me saying this. I'm trying to cram what I would normally try to teach in, I'll cover in an 85-minute class, checking homework, going over the lesson, answering questions, yada, 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 and as short of a video as possible to not bore you. However, I completely understand that I may be going extremely quickly, but remember, you have this video at your disposal. So right now, I would focus more on the learning aspect, and you can always go back and copy things down, rewatching the video again a second time, or however many you need to prep for your test. Okay, carrying on. The last aspect of today is graphing. And it directly relates to graphing our exponentials from a couple of classes ago. And here's why. If we graph the exponential, f of x is equal to 2 to the x power. So if you remember back when we were talking about your homework, if I wanted you to graph this and I wanted you to make a table of values to decide what points to graph, the very first question you need to ask yourself is, what makes the exponent 0? Well, if the exponent is just x, then obviously 0 does. So let's do that number. 2 to the 0 power is 1. Other good numbers to input are -1, 2 to the negative first power is 1/2, and then 2 to the positive first power is 2. So let's go ahead and sketch this. -1, of course it doesn't have to be perfect. Just maybe put some tick marks in each direction. So remember, this is the exponential. This is just a recap of what we've already known. If I graph these three coordinates, -1, 1/2, 0, 1, 1, 2 is going to look something like this. And of course, we know that there's an asymptote along the x-axis. If you remember what I said at the very beginning of this logarithms section, I said that logarithms were inverses to exponentials. So then if I want you to find the inverse, if I defined that exponential as f of x equals 2 to the x power, then I can find the inverse of that. If you remember finding the inverse, you simply just switch x and y. Well, even if I don't know the exact function or what the equation looks like, I can still make the table just switching x and y. So literally take these values and switch them. So instead of -1, 1/2, I'm going to have 1/2, -1, 1, 0, 2, 1. And let's graph these coordinates. 1/2 -1 will be about right here. 1, 0 will be here, and then 2, 1 will be here. And what you don't know yet, if I were to continue these, is that there would end up being, since the asymptote for the exponential is the equation y equals 0, right? That's the asymptote. Then that means the asymptote for the inverse is going to be x equals 0. So the asymptote for our logarithm is going to be the y-axis. And then if I were to finish it, that means this would get really, really, really close to the y-axis, but wouldn't actually touch it. And then we also have discussed last week that we know that inverses are going to be reflections over the line y equals x. So this diagonal line through the graph, these should be mirror images of one another. So that's how they're related. So now let's actually talk about what the log function looks like in isolation. Okay, so to recap, exponentials look like this. Your log looks like this. Okay, if I were to graph one of those in isolation, I might ask you, let's see, number 11, I want you to graph y equals log base 5 of x. Log base 5 of x. And what I recommend you doing is rewriting this in such a way that makes better sense to you. Logs are kind of hard to think about written the way that they are. So I recommend using our exponential converter, if you will, to write this using exponents instead. So I could rewrite this as 5 to the y power is equal to x. 5 to the y power is equal to x. And then I can create a table of values with this setup. So this time, just kind of know that you're starting with y. Usually we start with x, but if you think about it in terms of y, then I can say things like, okay, 5 to the, again, 0 power is a great place to start. That would be your y value, though. 5 to the 0 power is 1. 5 to the first, let me go backwards. 5 to the negative first power would be 1/5. And then 5 to the first power would be 5. So that's what, maybe I should have done this first. This middle one would be 5 to the 0, right? Y for 0 is equal to x is 1. This one's going to be 5 to the negative first is 1/5. And this one's 5 to the first is equal to 5. So that's where these values are coming from, plugging those in for x and y here. And then if I were to sketch a graph of that, again, you can now go ahead and know that the asymptote for each of these logarithms is going to be on the y-axis unless it has been transformed, which we'll get to that in a couple of examples. So if I were to graph these, 1, 2, 3, 4, 5, 6. Those coordinate points, 1/5 comma -1 would be something like this. Then 1, 0. Then 5, comma 1 would look like this. So there you have it. There's your logarithmic function, y equals log base 5 of x. Let's try another, number 12. Graph log, well, y equals log base 1/3 of x. So again, I recommend you rewriting that as 1/3 to the y power is equal to x. And then setting up our table based on that. So in our table, great number to plug in would probably be 0. 1/3 of the 0 power is 1. Go back a value, 1/3 to the negative first power is 3. 1/3 of the first power is 1/3. So sketching that function. I know I'm doing this very quickly, but I also know videos can be extremely boring, so I'm trying to make this go as quickly as I can, but still getting my point across. Okay, if I graph these coordinates, 1/3 comma 1, 1, 0, 3, -1. So notice this one was flipped the other direction because my base value was a value between 0 and 1. So it was reflected across the x-axis. Okay, 2 more, number 13. Same directions, I want you to graph this time y equals 3 times log base 10 of x plus 1. So obviously this one has complicated things slightly. So before I do anything, I want to write out in words the transformations that is occurring on this logarithm compared to usual. The 3 out front is a vertical dilation. 3 out front is a vertical dilation of 3. And then the plus 1 is going to be vertical shift up 1. And it's important to know that both of these are vertical changes, because then when I make my table, I'm going to affect the y values ultimately. So here's how you do something like this. You still start the same way that we just were. Create your x and your y t-chart. And still start with plugging in y values and working backwards. So at the core of it, we would say 10 to the y powers equal to x. We're going to ignore the excess stuff for a moment. And then we'd say, okay, we can plug in 0, and 10 to the 0 power is 1. We can plug in negative 1, and 10 to the negative first power is 1/10. And we can plug in 1, and 10 to the first power is 10. So this doesn't affect the x and the y. However, both of our transformations deal directly with the y values. So what that means is these y values technically aren't what we need to be plugging in. We need to dilate these y values by 3 and then add 1 to them. So we're going to make a third column with 3y plus 1. And you're going to use this expression with these values and plug them in. So if you plug in negative 1, 3 times negative 1 is negative 3 plus 1 is negative 2. 3 times 0 is 0 plus 1 is 1. And 3 times 1 is 3 plus 1 is 4. So what you've created now is you're going to use these x values and these y values to make the following ordered pairs to graph. 1/10, comma negative 2, 1, 1, and 10, 4. So you don't have to worry about doing all these transformations by hand visually, because you can do them directly in the table. Notice I didn't shift my graph to the left or to the right at all though, so my asymptote is still going to be along the y-axis. I need to make, I've got what, 10, 4, so I'm not going to be able to make that many tick marks. Well, maybe so. And I'll just try to graph as many of these points. 1/10 is just really small, so 1/10, comma negative 2 will look something kind of like this. 1, 1, and then 10, 4. 5, 6, 7, 8, 9, 10. Up 4 would be something like this. Okay, last type of problem, number 14. Same question, graph y is equal to 1/2 times the log base 1/4 of x minus 3. So similar to last time, in words, I want to write out what transformations are being done to this typical log function. Well, the 1/2 out front is a vertical dilation by 1/2. The base itself doesn't change a transformation. That just changes kind of the basic, not even the basic structure. That kind of changes the original stretch, if you will, or growth or decay of it, but that's not a transformation itself, so it really doesn't matter what your base is. X minus 3 is going to shift our function to the right 3. Shift it to the right 3. So again, what we're going to do is we're going to ignore those transformations at first, and we're just going to focus solely on the inside stuff, as if this were log base 1/4 of x. So then we would say 1/4 to what power would give us x. So that's what we're going to focus on first. And if I plug in numbers for y, again, plugging in 0 first would be great. Something to the 0 power is 1. Then to the negative first power, 1/4 to the negative first power is 4, and 1/4 to the first power is 1/4. So this takes care of the base x and the y. But what's different about this one compared to the last one is I have changes in the x's and the y's. Vertical dilation by 1/2 means that I need to dilate the y's by 1/2. So I'm going to make a third column over here and multiply these y values by 1/2. That's going to give me negative 1/2. 1/2 times 0 is still 0. 1/2 times 1 is 1/2. And then lastly, shifting to the right 3 means that I'm going to take these x values that I have here and I want to add 3 to them because I'm shifting everything to the right 3. So 4 plus 3 is 7. 1 plus 3 is 4. 1/4 plus 3 you can just say is 3.25. And then just like the last one, you take your outside columns, your final transformations that happened on the x and on the y, and graph those coordinates. 7, negative 1/2, 4, 0, 3.25, 1/2. And you would have a graph. 2, 3, 4, 5, 6, 7, 8, 9. That would look something kind of like this. Off the bat, because I shifted to the right 3, my vertical asymptote that's usually along the y-axis at 0 is now going to be shifted to the right 3. So that's a big obvious change. And then my coordinates, 7, negative 1/2, would be about here, 4, 0, 3.25, 1/2. So it's going to go in this direction. Well, that's a beautiful curve, huh? Awesome. Okay, I know this video was super lengthy. If you have questions, watch it again slowly, this time not being distracted by other things you may have been distracted by during class. Work on your review. I will post the answer key to the review at the end of the school day today with all of the solutions with it. That means next class, when you have a test on 8.1, 2, and 3, as long as you were able to do the review, you should be okay on doing well on that test. If you have any questions, shoot me an email or I should be hopefully back at school tomorrow. Drop by then so we can get you caught up and feeling good about doing well on this. Happy studying!